Hi everybody, Fus Muhammad Sharaf with you. Let's talk today about a new technique. It was sent by an engineering from Saudi Arabia. He would like to model it. He just schematic it to me, and I modeled it by the use of Simulink. So go to your destination folder, okay, and double clicking. Okay, your model should be appear like this. Okay, what's about this modeling for desalination? It's geothermal direct vapor generation for evaporation, condensation, distillation processes. The idea behind this is simple. We need to pump seawater through the condenser unit, and then we have to using geothermal well as a brine heater. So we are going to pumping seawater inside the well, despite of or regardless what is the problem behind this, what is the salt contaminants inside the well, what is the side effect of this operation. It's still under study, but we have to discover thermodynamically what is going on. So we are going to pumping seawater inside the well in order to rise up its temperature up to our desirable degree. So we have to decide the top steam temperature, and our assumption is that it's complete evaporation inside the earth. So we are going to catch up fully vaporized steam, and we will use it through, and we are going to condensate it in order to get our desalted water. And brine and saline water will stir in remaining in geothermal well. What is going on after that? It is not my specialization. I am just caring about how to model such technique, and we are going to continue our study about the side effects of pumping saline water inside the geothermal well and so on. All we are going to care about is it's a direct vapor generation for complete condensation. This is our main assumptions. Okay, for model information. Okay, you have to go to your model browser, okay, and check this, and check this here. Now this is our cycle. You have to click here. Okay, this is our cycle. It's simple, direct, and concentrated. We have here pumping unit, so we are going to double clicking on this block and assigning efficiency of the pump, early pump temperature, feed temperature, seawater temperature, and salinity ratio, part per million. Okay, because there is some effects of saline water on power or the process itself. And the second unit, because seawater stream is going to make or to act as a double acting process. It will cooling down the condenser for condensation processes, and we can use this preheated feed, because I think we can utilize this as a process before going to the geothermal well. We can use this stream for another desalination processes, maybe for another work recommendation or future work. We can deal with this. So we have here condenser unit. Condenser unit, we have to assign here some losses, minor losses, inner tube diameter, outer tube diameter, chill diameter, suppose it's 0.7. What about our flow rate? So suppose I'm going to desalinate 1500 meter cube per day. Ambient temperature, it's around 25. Okay, maybe 30 degrees Celsius. Okay, top cycle temperature, we need, what is the steam temperature? Sure, if you intended to go up more than 100, 200 and so on, you have to dig more in your geothermal well. So I do recommend 100 degrees Celsius, 80 degrees Celsius, quite normal for this. Condenser number of passes. If you increase your passes, you will increase your area. Okay, it has some effect on when you suppose it's 4 passes. I will keep this. Performance, I think going with lower efficiency, you can discover the effect. Going up to 1%, there is some complex calculation for effectiveness. It depends on your operating conditions. Suppose let's begin from 0.5. Okay. For geothermal, it's simple. We need just a steam pipe diameter in inch. You can assign this. You can assign ambient temperature and standards for geothermal. What is your standard? European standards or USA standards? I am going to use this one. Okay. Set your simulation time to 0. Okay, for single point running, and let's hit run here. It's simple, direct, and of course it's slower in efficiency because it's direct condensation. Okay, let's discover our results. First one is bump. As you can see here, we have, this is our pumping board. It's 0.7, nearly 0.7 kilowatts. Sure, if you increased your system productivity, it will harvest more power. This is specific power consumption. Okay, and we have here, this is well pressure loss to the evaporator, high pressure in bars. This is temperature of the feed, and this is total mass flow rate. Okay, total mass flow rate, we already assigned this. Okay, for condenser unit, okay, for condenser, as you can see here, I'm sorry, yes, we have cooling inlet and cooling outlet and steam inlet and condensate outlet. So we have 4 streams. Let's go inside here and discover. Okay, inlet steam temperature is 100. We already assigned this one, and cooling inlet temperature is 25, and we already assigned this one. So what is the outlet cooling stream? Outlet cooling stream, before going to the geothermal, it's around 62.5. We have enthalpy, we have pressure, and we have distillate temperature. Distillate temperature is this, the condensate temperature or distillate temperature. We have to calculate it. It's around 62.5 degrees Celsius. Enthalpy of the distillate, pressure outlet of the distillate, condenser area, number of tubes, tube lengths, condenser energy, this is heat rejection energy, and exergy destruction rate. In order to discover your result in signal processing or signal inspector, this button, in case if you are going to run your model under dynamic modeling, you have to go over here and check this box and double clicking, and we can write here I condenser in kilowatt or exergy destruction rate in kilowatt. Okay, so we will find this value in our signal processing signal inspector. For geothermal well, let's go for geothermal well. We have exergy destruction rate, inlet exergy stream, outlet exergy, and we have enthalpy of outlet stream. Okay, this enthalpy of the steam, and we have here, okay, well depth in feet, and we have diameter of the hole in inch, digging pipe casing diameter, geothermal well pressure, wellhead pressure, silica concentration, and we have here, this is for 100 degrees Celsius. We have to dig only for 100 around 300 meters according to US standards. For cost calculation, you can discover hourly cost for geothermal well, for condenser, for pump, for total hourly costs, total annual costs, and total water price. Okay, you can double clicking on your cost model and assign your plant lifetime, interest rates, load factor, and geothermal investment costs. Let it be around 1040, including digging and all stuff like this. So suppose I'm going for a dynamic model. I have to set my simulation time into infinity, and I would like to changing some parameters. Let's go for some parameters and hit run. Okay, double clicking. Let's go for changing productivity. I'm going to increase my productivity up to suppose it's for 5,000. Okay, 5,000 meter cube per day. Okay, okay, and number of passes in the condenser, 8 passes. Okay, top steam cycle temperature, I am going for, suppose it's up to 150. Okay, okay, let's increase our effectiveness up to 70 or 60. Okay, 70% effectiveness. Okay, let's increasing our salinity, increasing my salinity up to 40,000 ppm. Okay, it's quite good. Okay, that's enough for this. That's it, stop. Okay, let's go and see. I forget to discover geothermal well results in data inspector. I have to add this one. Okay, well, I'm sorry. Okay, for let's go for here for my results here. For data inspector, check here. Let's discover our results. Okay, for geothermal well hourly cost, as you can see, increasing your hourly cost because you increased your productivity rates and temperature, because you have to dig more. So dig more means more costs. Condenser costs, pumping costs, the same behavior, and we have here total hourly cost. This is your total hourly cost. Okay, total water price, fluctuating, specific power consumption of this is let's go in here. Okay, outlet water temperature into the well. Okay, this is outlet water temperature. I'm waiting. Okay, this is outlet water temperature, and distillate temperature as well. As you can see, there is a difference between both sides, and we have distillate enthalpy, and we have here a condenser area, increasing and decreasing, evaporator. This is mass flow rate of distillate. Okay, I forget to discover result effect on let's close this one. Let's go for geothermal well, and let's assign some outputs here. Suppose I'm going for well depth, so you have to check this one, double clicking in feet, double clicking and this one. Okay, remove this column, hole diameter casing, wellhead pressure. Let's go here and assign this one, silica concentrations, and well depth. I have to write here where depth in kilometers. Okay, well temperature, it's okay, and yes, inlet well temperature just coming from the pump, from the condenser after cooling. We can go here and assign this outlet cooling temperature. It's okay, it's already assigned. Okay, let's hit run again and trying to decreasing and see what is going on. Let's hit run. Okay, let's go here, trying to decreasing my productivity. Okay, down to lower values. Okay, 100 is enough, and decreasing our temperatures. No need for high rates of temperature because it's simple, down to 80, 90 degrees, decreasing number of passages in the condenser. Okay, decreasing my effectiveness down to 0.5. Okay, and let's go for salinity decreasing also. You can, I'm just demonstrating in order to show you what is the effect of changing. So I can change one parameter and get my results, change two parameters at the same time. Let's hit stop here. We can also add going here and look for signal for sources, and I can add signal builder block, so I can add many signals at the same time and controlling it at once in a specific limited time in order to get my results. Suppose it's in hours or minutes or seconds, I can control this one. Let's inspect our results. Okay, these are our results. Okay, this you can compare your runs because this is your order result. So as you can see here, this run number 2 and number 3. So as you can see, decreasing will cause decreasing for costs. As you can see here, condenser hourly costs, pump hourly costs, and totals. As you can see, you can compare between results on the same total water price, specific power consumption. Okay, and outlet temperature to the well. Okay, decreasing enthalpy of outlet, distillate enthalpy. Okay, well depths in feet. Okay, well depths in kilometers. As you can see here, still decreasing at well temperature, and we have here condenser area. Okay, so we are trying to say that we can model such things easily, and we can discover our results. It's this technique. So also I forget to tell you that you can send to the figure, or you can export your results outside this inspector, and you can deal with this in your workspace here. You can find your results if you type area condenser, you'll find your results here, or just double clicking, or you can drag and drop and click enter. Okay, finally, it's a simple technique, a direct vapor generation. Regardless what is the side effects of salt of saline brine inside the geothermal well, or effect on pipes, these things are still under study. Just thermodynamically, your model is fine, working fine, and our results are superb and accurate. Okay, you can also go in here for each block. You can double clicking, and you can edit your block, removing something, adding something, adding new parameter. These are your inputs, these are your function, and these are your outputs. So you can edit your model and reform it as well. Finally, I would like to thank you all about your interest in our model. Don't forget to like, share, subscribe. Thank you very much.